Hi, so we'll start in a couple of minutes so that a few more students can join the meeting. So, like it's 6:03 now, I'll start at 6:05. So, a few more can join. So it seems that no one else is joining the session as of now. So I guess I'll just get started with the problems since the time has already started. So yes, Nimitha, why did you are you raising your hand? Okay, cool. No worries. It was by mistake. So just to introduce myself again, so for the audience which is watching on YouTube, which would watch on YouTube, and for you, so hello, I am Lakshay Saggi, discrete maths problem solving TA for like the Tuesday 6 to 8 session for NPTEL. So this is the second session of the course. This is the second problem solving session. And in today's session, like we'll be discussing the problems related to more like first order predicate logic, and just we'll try to prove some stuff. Right? We should like try to prove some statements and stuff like that, because uh, we should know how to prove stuff, right? So we will learn how to apply the tools like induction and stuff for proving stuff. So yeah, so today's session will focus on proofs and a bit of first order predicate logic. So uh, I'll get started with the problems then, discussing the problems. So let me just share my screen, and like if you have any doubts while discussing the problems, you can just raise your hand or ask in chat directly. I'll try to answer to the best of my capabilities. So I hope my audio is clear as of now. So I'll just share my screen now and uh, okay, sure. Let me just share my screen for the questions. Okay, so I hope my screen is visible to you. So if it is not visible, you can call it out in chat. Otherwise, I'll just assume that it's visible. So yeah, the session will go like this. So I have some problem statements prepared. So like I have some 8 problem statements prepared. So I'll just discuss these problems and we'll try to solve these problems together. So everyone can understand like how do we approach problems and how do we prove stuff and stuff like that. So yeah. So we'll just get started with the same. So the first problem is saying let X be the set defining the days of the week and S be the set of students. Let M of S, for all S belong to capital S, be true when S is a member of the school library. And the predicate V S comma X be true when S visits the library on day X. So basically this predicate V denotes whether the student S has visited on day X in the library. So yeah. So which of the following expressions means that and this M of S means that S is a member of the library, right? So which of the following expression means that every student who is a member of the library visits the library on some day of the week? So basically, so we are given 2 types of predicates. So one predicate is which tells us whether a student S is a member of the library or not. And the second predicate, this V S comma X, means whether the student S visits the library on the day X or not. And now we want to write a predicate which states that every student who is a member of the library visits the library on some day of the week. So basically, what do we want to say? We want to say here that there exists a day in the week for every student. Basically, there exists a day in the week when the student has visited the library. Right. So I'll just type it out not in terms of symbols, but just in terms of basic notations. So and then we'll see which option sort of matches what I'm trying to say here. So for all, so what do we want? Let me just type it out. Yeah. So for all students, uh, there exists a day for all students which are member of library there exists a day on which maybe I should write for every student because for all it becomes a bit confusing. For every student who is a member of the library, sorry for that. There exists a day on which the student visits the library. So I just typed out this statement in a better form so that we can easily see what we want to do. So what we want to establish is that every student who is a member of the library, there should exist a day on which the student is visiting the library. And what we'll try to do is we'll just uh, we'll just go through these propositions and just see which of that proposition matches this sort of statement. So yeah. So let's just see. So first of all, we want for every student. So there should be a quantifier for for all students, right? So like for all students S, there should exist a day X such that student S, let's just look at the option D here. Or maybe yeah, let's just look at the option D here first. So for all students, there should exist a day, like for every student S, uh, there should exist a day X such that the student is a member, because for every student who is a member of the library, so every student M of S means that student S is the member of the library, and V of S comma X, the student S has visited the library on the day X. So option D is sort of correct here, because like what this means is that for all students S, or maybe option D is actually sorry, my bad. So what in option D is saying is that for all students S, there should exist a day, and the preposition here is M of S and V of S comma X. So M of S means that the student S is a member and the student goes to the library. But this is not exactly what we want. So basically what this sort of proposition is saying is that every student is a member of the library, because for all S we have this M of S type of term and V of S comma X. So this proposition D is saying something like for every student, there exists a day X and every student is a member of the library and the student visits on day X. So basically this option D's proposition is saying that every student is a member of the library and every student visits the library on some day X. But this is not what we want to say, right? Because every student need not be a member of the library. This M of S actually denotes the students who are actually the members. So what we want to prove is that every student who is a member of the library, there should exist a day for every student who is a member. The statement does not the question problem statement does not ask us that every student is a member. It says whoever is a member, that student should go to library on at least one day, right? But this option D is saying that every student is a member and every student goes on some day of the week. So option D is not quite correct. So similarly, let's see option C instead. So what option C is saying is that for all students S, there exists a day such that M of S implies V of S comma X. So what's the meaning of implication? So implication sign, as you must have seen in lectures also. So implication means that if the left part is true, then the right part should be true. So this sort of statement is saying for every student, there's the option C saying for every student S, there should exist a day X such that if the student is a member, like if M of F is true, M of S is true, then V of S comma X. So this option is saying that for all students S, there should exist a day such that if the student is a member of the library, then the student should visit the library on some day X. And this is something which we wanted to say, right? That for all students S, there should be a day such that if the student is a member of the library, that's what it's saying here, that for every student who is a member, every student need not be a member, but whoever is a member, for that student, there should exist a day on which the student visits the library. And this is precisely what this option C is saying, because it's saying that if M of S is true, if student is a member, then the student visits the library on day X. So I hope it's clear to everyone. If it is not clear, like you can stop me and you can just ask in chat if you have any doubt, or you can just raise your hand and I'll try to explain it again. So the correct answer here would be uh, option C. Maybe I just underline the correct answer also so that we can see. This is because this option C says that for whoever student who's a member of the library, for that student there should exist a day on which the student visits the library. And just for the sake of, like, I guess more understanding, like we are doing all of these problems just to understand more about predicate logic, right? So let's just see like what the, so we are right at the option C is the correct answer that we know. We should, I'm just saying that maybe we should see what option A and option B are also saying, just for the sake of clarity. Maybe I'll just type down also like what the all of these options are actually saying and what we wanted to say, why are they not correct. And so option D, we have already established that it says that every student is a member and goes to library on some day, which is not what we wanted. And option C is saying that if a student is a member, then he or she goes to library on some day. So these two statements we established, and we have seen that option C is actually the correct answer. Now let's just see this option A here. So option A here says that so what's the option A saying? Let's just see for the sake of better understanding. So here this option A is saying that there exists an X, and for all S, M of S implies V of S comma X. So we just see that this proposition is actually similar to option C. Here the proposition inside is similar, like M of S implies V of S comma X. But the ordering of these quantifiers is different. Like there exists an X, and for all S are switched in between option A and option C. So first of all, a heads up that uh, changing the ordering of these quantifiers can change the meaning of the whole expression. So be careful with that. So option A and option C may or may not be equivalent. Like it's not a guarantee that both of these will be equivalent. So we'll just see what the option A is trying to say here. So option A, there exists X quantifier comes first, right? So what this means is that there exists a day X such that all students, now the inside part is for all S, M of S implies V of S comma X, right? So the part inside of this is saying that, so this part is saying that there exists a day, and the inside part is saying that uh, if a student is member of the library, then that student visits on the day X, right? So do you see why this statement is actually wrong? It's not what we wanted to actually convey. because the there exists X part is actually outside. So what it's saying is that we first pick some day, let's say Friday, and then it says that there for all students S, like whoever is a member visits the library on that day X. So this option A statement is sort of saying that there exists a day, let's say Monday, Tuesday, Wednesday, Thursday, or let's say just Wednesday. So there is a day, like let's say Wednesday, and every student who is a member visits on Wednesday, which is not what we wanted to prove, right? Uh, we wanted to say that every student visits on some day of the week, but for all the students, that day need not necessarily be the same, right? Student one, member one can visit on Monday, member two can visit on Tuesday, member three can visit on Wednesday, and that will work for us because in the original problem statement. But this option, what option A is saying is that every student who is a member visits on some fixed day. Like there is a day, let's say Wednesday, and every student visits on Wednesday. So this is something which we not did not actually want, right? So that's why this option A is sort of incorrect. So just changing these ordering of these quantifiers also changes the whole meanings sometimes. So be careful with changing and or reordering these quantifiers, I would say. So yeah. So I'll just see that what option is trying to convey. So option A is trying to convey that there exists a day such that every member visits on that day. So maybe there is a day X such that every member visits on day X, which is actually not what we want, right? So yeah. Now let's just see what option B is also saying. So here option B is saying that there exists an X such that for all S, M of S and V of S comma X. So this is the quantifiers inside are similar to option D here. And option D was saying that every student is a member and goes to library on some day. But now what this is saying is that here again the day is quantified. There exists a day quantifier is outside. So we are fixing the day first. So it's saying that there exists a day, let's say just say Wednesday, like so there exists a day such that for all the students, a student is a member as well as the student goes on that day X. So this statement is sort of wrong on so many levels. It's saying that every student should be a member and every student visits on the day X. There exists a day on which every student is visiting and every student is also a member. So this statement is sort of wrong on so many levels, like if you see what I mean. So what this is saying is that that every student is a member and visits on day X. So yeah. So it's sort of saying that there's a day X such that every student is a member. So basically it's saying that every student is a member of the library and visits on day X. So this is something which we not wanted, which we did not want to convey, right? So that's why this option C is the correct answer here. So I hope you understood what I was trying to say here. So now let's come to question 2 then. So I hope this was clear, and if this was not clear, like you can just ask me in chat if you have any doubts, and I'll try to answer it. So yeah. So the second question is a bit interesting. So it's saying that we want to prove or disprove this statement that if x is irrational, then x to the power y is irrational for all real numbers y. Okay, maybe this statement is a bit trivial. Maybe what I wanted to say was for all irrational numbers. Yeah. So what we want to prove or disprove the claim is that if x is irrational, then x to the power y is irrational for for all irrational numbers y. So what it's saying is that basically any irrational number raised to a power an irrational number is irrational. So do you see this claim? So basically the claim here is basically an irrational number raised to power another irrational number will always be irrational. So we want to see whether this is, so we want to either prove this fact that irrational raised to the power irrational is always irrational, or we want to disprove this fact. So we want to disprove, we'll want to see an instance where irrational raised to power irrational will actually give output as a rational number and not an irrational number. So I hope you understand the question itself. So the question is just we want to see whether irrational raised to power irrational can be rational or is it always irrational. So what do you think intuitively, like an irrational raised to the power irrational number, will it always be rational or can it be rational? So what does your intuition tell you, Nimitha? Yeah, not sure. No issues. So sometimes for some people, the intuition sometimes says that if we are raising an irrational number to a power irrational number to an irrational number power, then the result should be irrational also because irrational raised to power irrational, how can it be rational? But actually, interesting fact is that this is incorrect. Like this claim is incorrect. So we will disprove the claim. So just a heads up. So how do we prove something? To prove something, we give out a detailed explanation on, like, we basically write a proof that why is this thing correct actually. And to disprove something, sometimes all we need is just one example where this thing does not hold. So if we can give just one example where this statement does not hold, then we have disproved this statement. But for proving this statement, we actually need to say that for all possible examples, this will be true. So generally, proof is a bit more drawn out because in proofs we have to cover all the cases. But to disprove something, we just want to give one example where this claim does not hold. So this is actually a very interesting question. So I believe like you should pay attention to this. So what this basically means is, so we will disprove the claim. So what this means is that uh, we will show an instance where an irrational number raised to power irrational number gives and gives a rational number. So irrational, we show an instance where irrational we should write it as like this gives a rational. Yeah. So we show an instance where an irrational number raised to an irrational power gives a rational number. And so this is something which is like, personally, I like this question a lot because I feel this is very counterintuitive something. So For this, let's just take the example as this. So let's just consider the number root 2. So I'll write root 2 as something like this sqrt2. So what do we know is that let's just consider a number like let's say consider a number x is equal to root 2. So we know that this is irrational, right? We know that root 2 is irrational. So we know that x is irrational. So now what we do is consider a number like let's say we consider a number y, which is equals to root 2 raised to the power root 2. So let's just consider this number, which is like root 2 raised to the power root 2. So basically, y is a number which is like an root 2 is irrational. So it's something like irrational raised to the power irrational. And what we want to actually prove is that there exists an instance where irrational number raised to irrational number gives a rational number. So like what we want to say is if y was like if this number was irrational, like I don't know if this root 2 raised to power root 2 is irrational or irrational. I don't know. Okay. But let's just say so there can only be two cases, right? Whether it is rational or it can be irrational. Right. So if it is rational, I don't know. We don't know if like I personally don't know, and I won't be proving whether y is rational or irrational. So I'll just do some case analysis. We don't know if y is rational or irrational, right? So we will consider cases. So case one is y is rational. So if this number root 2 raised to the power root 2 is actually rational, then I'm claiming that I have actually disproved this. Basically, I have shown an instance where an irrational number raised to the power irrational number gives a rational number. Because root 2 was irrational, this root 2 was irrational. But now if I've assumed that y is rational, so basically what I have proved is that an irrational number raised to power irrational number has outputted rational number. So we are done. So in this case, we are done as we show as irrational, or maybe just as x that raised to power x gives a rational. So in this case, we are done. So, but let's just consider case two. Like we don't know if y is rational or irrational, right? So we'll consider both the cases. So suppose if this y, this number was irrational, actually. So let's just say y was irrational. So in this case, what we can do is something very interesting. So now let's just consider another number, which is like in this case, consider a number z equals to y raised to the power, like basically y raised to the power square root 2. So earlier we took some number root 2, then we raised it to the power root 2. And what I'm saying is if you again obtain an irrational number, then just raise it again to the power root 2. So, uh, so what we are doing here is quite simple. So basically what Z is, what actually Z here becomes is, so I'll just write that. So Z is actually equals to basically root 2. So putting in y as root 2 raised to the power root 2. So Z just becomes root 2 raised to the power root 2, and which is again raised to the power root 2 because this was y, and we are raising this y again to the power root 2. So we know that if we raise this number to another power, then by the rules of basically uh, like power raising of rational numbers, so we know that number x raised to the power a and whole raised to the power b will actually be equal to x raised to the power ab, right? So basically what I'm trying to say here is, so what we are actually doing is we are taking this number y and we are again raising it to the power root 2. But we know by the rules of rational numbers that this is actually equals to, so basically the indices, like the powers, will actually get multiplied here. So what this actually becomes is root 2 uh, raised to the power root 2 times root 2. So these SQ is this root 2 and this root 2 will get multiplied. So this will actually become equal to root 2 times root 2. And root 2 into root 2 is actually equal to 2 itself, right? So this actually becomes equals to square root 2 raised to the power 2. And what is root 2 square? So root 2 square is actually 2 itself. So we have obtained a rational number here. Z is a rational number, right? Because 2 is rational. So I'll just say that so Z is rational, right? So what this means is that in this case, what did I do? I took an irrational number y because I assumed that y is irrational, and I raised it to the power root 2, which is again an irrational number. But the output was actually 2, which is a rational number. So even if y was irrational, what we have obtained is raising this irrational number to another irrational power root 2 will actually give an output as a rational number. And this is what we wanted to show, right? We will show an instance where irrational number raised to power irrational number gives a rational number as output. So in this case also, we have actually shown that. So in this case also, we have shown that irrational number, and here the irrational number was y, raised to power, raised to an irrational power, and here the power was root 2, gives a rational number output, gives a rational output, and the output here was 2. So here also hence in this case also, hence we are done in this case also. So I hope you get what I was trying to do here. Basically, so the main beauty, like why I like this proof, is that the main beauty of this proof is that this number root 2 raised to the power root 2, I took this number, and we don't need to know whether this number is rational or irrational, because proving whether this is rational or irrational is itself a huge task, right? So we don't know whether it is rational or irrational number, but we just assume, like suppose it was rational, then also our proof is done. And if it was irrational, then if we raise it to again a power of root 2, then our proof will be done. So that's why uh, I really like this proof, because like, it's a very cute proof, because we don't need to know whether y is rational or irrational, whether this number is rational or irrational. We can just take the cases and handle both the cases accordingly. So that's the beauty of this proof. So yeah, hence this proof. Just underline this in the end. Yeah. So if there are any doubts, you can ask me in chat. Otherwise, I'll just proceed to the next question now. Let me just go to the page. So yeah. So yeah. So the third question is actually, so Alice and Bob are playing a game with a pile of n stones. They take turns with, so basically they are playing a turn-based game where always Alice is starting. And the rule of the game is like there's a pile of n stones, and each player can take up to x number of stones from the pile, and x will be given to us like according to the options, like there will be different cases of x. So let's just suppose a player can take x stones from the pile during its turn, and now each player must take at least one stone from the pile at their turn. So maximum number of stones you can take is x, minimum is 1. So if a person cannot remove any more stones from the pile, they lose. So when can a person not remove any more stones from the pile? When there are 0 stones left, right? So suppose that there was only one stone initially in the pile, and Alice is starting, so Alice takes away the initial one stone. Then there are 0 stones left. So Bob cannot pick any stone from the pile. So Bob loses and Alice wins. So this is sort of the game. So suppose there was only one stone, then Alice just takes that stone and Bob is left with no stone to pick. And so Bob loses and Alice wins. So now we want to see whether Alice will win or Bob will win. So winning criteria of Alice and Bob will differ on the values of n and x, the values of n and x which are given to us. So when some n is like when n and x, like for different values of n and x, like different winners will arise. Sometimes Alice will win, sometimes Bob will win. So a very high level idea, like first of all, what I wanted you guys to see here was that so I'll just give a high level idea first of all and then discuss the options. So for this problem, a very high level idea is what I'll claim is, or maybe not just high level idea, I'll just write a claim. So the claim is if the pile of n stones, if the number of stones is like, let's say if n is less than equal to x, then Alice always wins. So also, yeah, we can take any variable, Nimita. So n can be 6, x can be something. But for general n and x, I'll just be writing out some properties. So yeah. So first of all, we'll also be assuming that every player plays smartly, like they are playing to win. So they move their best move and don't just make any dumb moves. So yeah. So my claim is that if n is less than equal to x, so basically n was the number of stones in the pile and x was the maximum number of stones which a person can pick, then I'm saying that Alice always wins. And why is this true? Do you guys see why this claim is true? That if n is less than equal to x, then Alice will always win. Note that Alice is always the one who's starting. So let's just take an example. If n was 5 and let's say x was 6. So what will happen is so the number of stones in the pile are only 5, but Alice can pick maximum 6 stones at one go. So Alice can also pick 5 stones, right? The maximum is x and minimum you can pick is 1. So Alice can pick all the n stones, like all the 5 stones by herself. And now in Bob's turn, Bob is left with 0 stones to pick because Alice has took all the stones. So that's why Alice will always be the winner here. This is true because Alice can pick all the stones in her first try itself. So what I'm like, why I'm doing this sort of stuff, I'm just trying to make you guys understand the structure behind this problem. So every problem need not follow this sort of structure, but this sort of starting rounds on which you can start to think about any problem. So yeah. So how do we start to think about any problem? So we start from smaller cases and see like how the problem is behaving actually, and then we generalize it for further cases. Right. So we know that if n was actually less than equal to x, then we can easily always answer that Alice will win. So suppose n was given as 5, x was given as 10, 20, whatever, then we can just blindly say that Alice will win. So now we want to see what happens when n is actually greater than x. Right? So if n is greater than x, let's just say if n was actually x plus 1, what will happen? So if n was x plus 1 actually, uh, then we know that Alice can't pick all the stones, right? Because Alice can pick only X stones maximum. And Alice also has to pick one stone at least. So do you see where this problem is going? So as soon as Alice picks, as soon as Alice picks at least one stone, so Alice will have to pick one stone, right? And it can't pick all the stones because Alice can pick maximum X stones. So there will be at most one stone left in the pile. So what will happen is on a high level, you can just see that. So suppose n was, let's say 6 and x was equals to 5. So Alice can pick one stone, two stone, three stone, four stone, or five stone. So in all the cases, the number of stones will be between 1 to 5. Like if Alice picks only one stone and the initial n was 6, so after Alice's turn, the number of stones left will be 5 only. And similarly, if Alice picks two stones initially, then the number of stones left will be 4. Similarly, if Alice picks three stones, then it will be 3. And if Alice picks one stone, the number of stones remaining will be 5. So the number of stones remaining are after Alice's turn between 1 to 5. So now what I'm claiming is that now Bob can always win. Do you see why? This is because like just the role of Alice and Bob has reversed, and like the now the stones, the n has become now less than equal to x because the number of remaining stones have become less than equal to x because x was 5. So now the remaining stones have become less than equal to 5. So now Bob can pick all the stones in one go, right? So now Bob can pick all the stones in one go, and now in Alice's turn, Alice won't have any stones left to pick. So this is sort of the argument. Maybe I'll just write it down so that you can understand actually what's happening. So as soon as Alice picks at least one stone, number of stones left in the pile will be between 1 and x. Right. So now Bob can pick all these stones, just like what Alice did here. We have to pick it number stone. So now Bob can pick all these stones, and Alice won't have any stones left. Stones left. Hence, Bob wins here. So Bob is in the case if n is equal to x plus 1. So we are assuming that they play smartly. So we see here that however smartly Alice plays here, the Bob will always be able to win if Bob is smart. So yeah, sometimes even if you do play smartly, things are out of your control and you can lose the game. So yeah. So this is something. So if n is so Similarly, if n was actually equal to x plus 2, so now I'll just write, now this is a bit of an interesting argument. Let's just say if n was equal to x plus 2, then what can we do? If n was x plus 2, now Alice is starting, right? So let's just say, I'll say Alice only picks one stone. Alice only picks one stone. And now what happens is the number of stones left in the pile will be x plus 1. Now number of stones left in pile is equals to x plus 1 now. And now, do you see what happens here? So we prove that if number of stones left in pile is x plus 1, then Bob wins. But this was based on the fact that Alice picks the stone first, right? So if n was equal, if number of stones was equal to x plus 1 and Alice was picking first, then Bob wins. So I hope you see what was happening in this case. So there were x plus 1 stones and Alice was picking first and Bob was winning. But now in this case, Alice has already picked one stone. Now the number of stones left in the pile is x plus 1, which is again equal to this x plus 1. But now the role of Alice and Bob has switched, because earlier we said that Alice was the one who's speaking first. But now since Alice has already had her turn, so now Bob will pick. So do you see? So earlier, if if number of stones was x plus 1 and Alice was picking, then Alice was losing. So similarly here, if number of stones are here x plus 1 and now Bob is picking, so Bob will lose. So I hope you see the argument here. So the number of stones left now, Bob will have to pick some stones. This is similar to the n equals to x plus 1 case, except that Bob moves first. Bob moves first here instead of Alice. So earlier, so when number of stones left are x plus 1, in that case actually Bob is actually moving first, because Alice has already moved and picked one stone here. So hence, so earlier Alice was losing when she was moving first. So now Bob is moving first here. So hence roles of Alice and Bob are reversed. And so Alice wins. So this is a bit tricky argument, but okay. So Nimita, you're saying, can you please explain how Alice wins in second? So in the second case was this n equals to 6 plus 1, right? N equal to x plus 1. Do you want me to explain? Here Bob was winning, not Alice. Yeah. So this n equals to x plus 2 thing, right? So this is what we are trying to say. So let's just say there are two people like Alice and Bob. Like I'll just try to type it out. Alice, Bob. And what's happening is they are playing a turn-based game where, let's say, the first turn Alice, let's just make a sequence. So first Alice moves, then Bob moves, then Alice moves, then Bob moves, and again Alice moves, and so on. So the moving order is basically A B A B A B A B. I'll just write that. So they move in this like in this way. Like first Alice will move, then Bob moves, and A moves, B moves, and so on. But what I'm trying to say is that these Alice and Bob are just names of the people, right? These are just placeholders. So I could have just named the first person, like here I have named the person who moves first as Alice and the person who moves second as Bob. I could have also called the first person who moves as Bob and the second person who moves as Alice. So these are just names or just placeholders for the people, right? The main thing which they are identified is with the fact that the person is moving first and the person who is moving second. Right. So let's just keep this in mind that Alice and Bob are just placeholder names for people. And the main property for these people are that one person who moves first and the one person who moves second. Right. So now here, if n equals to x plus 1, if n was equal to x plus 1, here we had established that Bob wins. So basically, we had established that if n was equal to x plus 1, then the person moving second will win. Right? So if n was equal to x plus 1, then the person who moves second will win. Now, what I'm saying is, if n was actually equal to x plus 2, in this case, I'm claiming that the person who moves first will always win. And how is this true that the person who moves first will always win? This is true because the person, Alice is just the person who moves first, right? So let's just say the person who moves first, she has a choice, Alice has a choice how many stones she wants to pick. So let's just say she only picks one stone. So after she picks one stone, let's just see the scenario after this. So earlier, initially, there were x plus 2 stones, right? As soon as Alice picks one stone, the number of stones now left in the pile are x plus 1, right? And now we can think of this as a new game. Now we can think of this as a new game where Bob moves first. From here on, we can think of. So basically, initially Alice was moving, right? So Alice has already moved, and after this, there are x plus 1 stones left. So now the remaining sequence can be thought of as a now the remaining sequence of move can be thought of as a new sequence, right? In which initially we like at this point after this A, before this A, we had like x plus 2 stones, and just after A, we have x plus 1 stones. And now from these, like we can think of this as a completely new instance of a problem where like we have like this after Alice has moved her one step, now this becomes obsolete, right? The only remaining fact which is important to us is that the number of stones now have become x plus 1. So now number of stones have become x plus 1. And now we have another sequence of moves. And in this sequence of moves, Bob will move first. Because in actuality, Alice was moving first. But as Alice has already moved, so now is the turn of Bob. And we can just say that instead of like, if we just remove the initial move of Alice, and we just say that we are starting with x plus 1 stones instead of x plus 2 stones, now the problem becomes identical. That's what I'm trying to say. That initially we had x plus 2 stones and Alice was moving first. But if Alice has already picked one stone, now Alice's turn is over. So now Bob will have to move. And there are only x plus 1 stones left. So I can think of this as a completely new problem in which we were starting with x plus 1 stones. We can think of this as a new game with x plus 1 stones where Bob moves first. Uh, do you understand what I'm trying to say, Nimita? Okay, you got it. Nice. So now we are basically thinking of this as a new game which has x plus 1 stones, where Bob is moving first. So now Bob will have to pick some stones, like as Alice had to pick because Bob is also moving first. Now this is similar to the n equal to x plus 1 case, except that Bob is moving first here instead of Alice, right? We have x plus 1 stones, but here in x plus 1, Alice was moving first. But here, Bob is moving first. And I just said that Alice and Bob are just placeholders for people who are moving first and moving second. So roles of Alice and Bob are reversed. And so here, like in this case, Bob was winning. So in this case, Alice will win because uh, Alice was moving first here and was losing. So here, Bob was moving first. And so Bob will lose. So Alice wins. So I hope it's clear to you. So similarly, if n equals to x plus 3, then like basically for all these cases, I'll sort of leave this as sort of an exercise to you. Like try it yourself. What happens in other cases? Okay. So you will get some hint from like these problems only. Like I'll also show you like for all these cases n equal to 6 and x equal to 3, what will happen. And maybe you can derive some hint from that, what will happen in all general cases. So I have given a basic layout of like how do we approach these sorts of problems. And now I'll just try to solve for these examples. And maybe from that you can generalize for all the cases. Like I only generalize till n equals to x plus 2. But for n equal to x plus 3, x plus 4, x plus 5, like what happens, I'll try. You guys can figure it out yourself using just this sort of recipe and the type of solution which I'll be following to solve these examples. So let's just say we are trying to solve. So for option A and option B, like we just have to decide for n equal to 6 and x equal to 3, whether Alice wins or Bob wins. So one of Alice or Bob will win. So we just have to decide whether in n equal to 6, x equal to 3, uh, who wins, right? So this is the case which we want to solve for our problem. So I'm sort of claiming that this will be similar to this type of argument here. Note that if n was equal to x plus 1, then Bob will always win, right? So if n was in n equals to x plus 2 case, what did Alice do smartly? Alice only picked one stone so that the n equals to x plus 1 case arises, and Alice and now Bob will have to pick first. And so Bob will lose. Right here, the smart step taken by Alice was to just pick one stone. So she tried to reduce this x plus 2 case to this x plus 1 case. And that's how she won. And that's a 100% sure shot way that Alice will ensure herself a victory. So what I'm claiming is that this sort of strategy by Alice will work here also. How instead of like here Alice, like the main strategy of Alice was here was just take from this, like just try to reduce the initial number of stones to x plus 1. Because as soon as she reduces the stones to x plus 1, then she has a sure shot victory. Right. So here now again Alice will try. So here to make it x plus 1, Alice remove one stone. Now here to make to what is the value of x? X is 3. So x plus 1 will be equal to 4. So now to make the number of stones equal to 4, what can Alice do? Initial number of stones is 6, and Alice wants to make the number of stones. If Alice wants to make the number of stones equal to 4, how many stones will Alice need to pick? Nimita? So what do you think? How many stones will Alice need to pick to go from this n equal to 6 to the 4 case? 3. Yeah, 2. Yeah, you're correct. So yeah, uh, if Alice picks 2 stones, then she always wins. Yeah. And why is this the case? This is because after Alice moves, number of stones become equal to 4, which is x plus 1. Now following similar reasoning to n equals to x plus 2 case, Alice wins here. So yeah. So Alice has a sure shot way of winning by picking two stones here. Yeah, Alice wins here. So Bob has no chance of winning because like, Alice can pick just two stones, and after that, it's a loss for Bob. So for this case, Alice wins. So like option A is correct. And now between option C and option D, so another case they are asking is uh, n equals to 5 and x equals to 4. So what I'm claiming is we have already discussed uh, this sort of case in our previous discussions. So can you answer, Nimita, who will win here, Alice or Bob? Maybe you can just try if you feel comfortable. Like I'm saying that we have discussed this case actually in these sorts of things. Okay, you're typing something. Okay, maybe. Okay, you want to think about it. Okay. Oh, so Nimita is saying Bob wins. So yes, actually you are correct, Nimita. So just this, you can see that n is equal to 5 and x is equals to 4. So this is just this case, the n equals to x plus 1 case. And we had already seen that if n equals to x plus 1, then Bob wins. So yeah, this is just the n equals to x plus 1 case where Bob wins. We have already discussed this. So in this, Bob will win. So the correct answers are for n equal to 6, x equal to 3, Alice wins, and n equal to 5, x equal to 4, Bob wins. So the correct answer is option A and option D. Correct answer. Option A, comma D. So in this case, Bob is winning and that's so yeah. So I hope it's clear to you. So now let's just come to fourth question. Fourth is a bit relaxing question, like it's easier than all these previous questions which we were discussing. So you might feel a bit relaxed here. Yeah. Uh, so question 4 is just straightforward, related to rule of inference and stuff, whether you can apply the implications and stuff directly. So the question is, due to increasing COVID cases, like this is a bit old question. So when COVID was actually prominent. So yeah. So due to increasing COVID cases, new restrictions were introduced in a school. If any student in a class tested positive, then that student must be isolated. So note that the if condition, like a student is like if a student tested positive, then he or she must be isolated. Also, if a COVID positive student was in contact with more than 5 students in class, then all students must be isolated. So if a COVID positive student was in contact with if a COVID positive student, the key here is COVID positive student was in contact with more than 5 students, then all the students of the class must be isolated. Okay, so these are two types of rules which have been introduced in school. And now let's say Ajay in class 10th B has tested positive. And now what we want to determine is what can be inferred from this information. So the rules say that if any student is tested positive, then that student must be isolated. And if a COVID positive student was in contact with more than 5 students in class, then all the students in the class must be isolated. So these are the two rules. And now we know that Ajay has tested positive. So choose the statement which can be inferred from the above. So one thing like we can just see straightforward is that Ajay has tested positive, and since any student who tested positive, that student must be isolated. So it means that Ajay must be isolated, right? So at least Ajay is isolated. We know that in this question. So another thing is we don't know if Ajay has come in contact with other students or not. Like Ajay was a COVID positive student. If he was in contact with more than 5 students in class, then all the students must be isolated. But we don't know if Ajay came in contact or not because it's not given in the question, right? So the first option says all students in class 10B must be isolated. So this option is not quite correct because all students would be isolated when like a COVID positive student was in contact with more than 5 students. And we know Ajay was COVID positive, but we don't know if Ajay came in contact with more than 5 students or not, right? So we are not sure that this is true or not. So this statement we can't be definitely said that all students must be isolated. We can only say that Ajay must be isolated, but we don't know if other students should be isolated or not. So the second question says that second option says that some student in 10th B must be isolated. So this statement is correct because some student in 10th B must be isolated. And who is that student? The some student here. Who is the student who must be isolated? No contact. We don't know if any student has come in contact. So, so Nimita, we don't know if any student came in contact with Ajay or not, right? So we don't know if we need to, uh, like what we know for sure is Ajay is COVID positive, right? In the question, the only thing which we know for sure is Ajay has tested positive. So Ajay has tested positive, so Ajay must be isolated. But we don't know if Ajay came in contact with others or not. So we can't say anything about anyone else. We can just say statement about Ajay. So we can say that Ajay must be isolated. And so who is this some student in 10th B? That some student is Ajay. Is it clear? Yeah, okay, clear. Nice. So yeah. So all students is wrong because we don't know if what's the condition for other students, but we definitely know the condition for Ajay, who is some student of 10th B, right? So correct in answer. So option B is at least correct. So I'll just write, since this is the more straightforward question, I'll just write the correct answer here and not mention the all the and not type out all the reasoning and stuff. Because I think like these oral discussions are enough for this question. So yeah. So option A is incorrect. Option B, some student in 10th B must be isolated is correct because this some student who is isolated is Ajay actually. Option C is all students in 10th B tested positive. Like this statement is also like this statement is also like this statement can't be inferred from the above abstract, right? Because we don't know anything about all the students. We just know that Ajay has tested positive. So option C is incorrect. And option D is if some student was in contact with more than 5 students, then all students must be isolated. So is this statement correct or can this statement be inferred? Nimita, according to you, is it correct or not? It's correct. Okay. So one thing to look at is I thought so that one might get confused. So if some student was so what this statement is saying was if some student was in contact with more than 5 students, then all students must be isolated. But the restrictions actually say that if a COVID positive student was in contact with more than 5 students. So suppose the student who came in contact with more than 5 students was not Ajay and let's say some other student, Rajiv, who was actually not positive. So Rajiv came in contact with 5 students. So Rajiv shook hands with 5 students. But in that case, there is no issue, right? Because Rajiv is uh, non-COVID positive. Only Ajay we know for sure is COVID positive. So if yeah, yeah. So yeah, so this some student can be any student, right? Here, this some student referred to Ajay, but this instantiation of some student can be any student, right? Actually. So this is there was student Raji, and for Raji, it could be the case that Raji was not COVID positive and came in contact with 5 students. Then it's not an issue for class, right? Maybe Ajay did not come in contact with any student, but Rajiv came. So in that case, there won't be an issue. So this option is also incorrect. So the only correct answer is option B. Yeah, exactly. It can be any. So it need not be actually Ajay. So yeah, this was a bit of a trickier option. And I thought that some might get confused because of this. So yeah, Nimitha is typing something. So but same way the option B. Okay. So Nimitha, let's just see like what these quantifiers actually mean. Like let's just first make it clear what the quantifiers actually mean. So some student in 10th B must be isolated. So what does this statement mean? This means that there exists a student in 10th B who must be isolated. So what we want to like this statement like option B will be true if there exists at least one student who must be isolated, right? And we know that there exists at least one student who is isolated and that student is Ajay. Like it's not that you can replace this some student by any name, like you can replace it by Ajay or Rajiv or anything. It's just that at least one student should have this property. At least one student should be intently must be isolated. And here we know that Ajay must be isolated. So this option B is true. Now in option D says that uh, like if some student was in contact with 5 students, then all students must be isolated. Like we don't know for like we don't know the student, right? Who was in contact. Similarly, here also we don't know the student. Like in this statement, some student in 10B must be isolated. We don't know the student. Maybe there were 10 students who must be isolated. Like maybe Raj, maybe another student, Raj, was also isolated. But we know for sure that at least Ajay was isolated. And that's why this statement was correct because at least Ajay is isolated. Maybe there are more students who must be isolated. But at least for Ajay, this is correct. Now here in option D, if some student was in contact with more than 5 students, then all students must be isolated. Now, like similar reasoning applies here. So if some student was in contact with more than 5 students, then all students in 10th B must be isolated. Now we don't know some student, right? That some student can be Rajiv, can be Ajay, can be anyone. So what we want to ensure is that uh, there should exist at least one student who was in contact with more than 5 students, and then all the students must be isolated, right? But that some student can be anyone. It can be Rajiv, it can be Ajay, it can be any student. It need not be Ajay exactly. Like same way in option B, it need not be Ajay that like who must be isolated. There can be more students also, but we know for sure that at least Ajay is isolated. Here, uh, the language is a bit different. Here what we are trying to say is that Here again, like here also some student was in contact. We don't know which student, but if some student was in contact, then all student must be isolated. But here, if that some student was actually Rajiv or someone else, like here we know for sure that Ajay was isolated. So we could have replaced this some student by Ajay. But here we don't know for sure in this option D whether Ajay came in contact with more than 5 students, right? If we knew for sure from the abstract that Ajay was in contact with 5 students, then here we could have replaced this some student by Ajay. But here we don't know whether Ajay came in contact. So maybe Ajay came in contact, or maybe Rajiv came in contact, like maybe Rajiv came in contact with 5 students or anyone. And that's why here we can't say for sure that all the students must be isolated. So maybe Rajiv came in contact, and then the student need not be isolated because Rajiv was not COVID positive. But in option B, we know for sure that Ajay must be isolated because Ajay had tested positive. But in option D, we don't know for sure if Ajay came in contact with more than 5 students. The student who came in contact with 5 students might have been Rajiv and not Ajay. So is the distinction clear? Yeah, it is important to pay attention to words and logic. Exactly. Because like the predicate logic actually is very straightforward. Like the you like yeah, one beauty of predicate logic, you don't need to pay attention much to the language, but you need to pay attention to the quantifiers and the main thing which they are trying to say. So here it's trying to say some student in 10B must be isolated. So what does some student mean? So at least one student should exist. Here also, it is saying if some student, but here also that some student can be any student. But from the given abstract, we know that for sure that in option B, the some student can be that student Ajay itself. But for option D, we don't know from the abstract that that student must be Ajay. So yeah, it's important to pay attention to the logic and what can you derive from the given abstract and what can't be derived from the given abstract. So yeah, exactly. So no issues, Nimitha. You can ask questions anytime you want. Like personally, I prefer like even if like we cover lesser number of questions, I prefer that we cover the questions which are discussed properly. Like everyone is able to understand properly, like what I am trying to say, rather than doing a lot of questions and not understanding much. It's much better to uh, do lesser amount of questions, but discuss them properly. So this sort of problem, there's no specific name for this problem, Nimita. It's just like maybe like it's just like finding out the what possible inferences can be derived from uh, a given abstract. So yeah, maybe you can just say like there's no specific name for this problem as such, but the problem is just like deriving the correct inferences from given information. So we have given some information and we want to derive some inferences. So yeah. So is this clear to you, Nimita, or should I explain it a bit more? Okay, it's clear. Nice. So let's move on to the next question then. So fifth question is also, I believe, a bit slightly on the easier side. So sixth question is a sort of question which we have been doing, similar questions we have been doing since high school. So I don't think there'll be much trouble. So saying that consider a number which is of the form 4k plus r. And so we know that any number can be written as like basically divide the divisor into quotient plus remainder, where remainder is between 0 and the divisor itself. So if the divisor is 4, then any number can be written in form 4k plus r, where r will be between 0 to 3. And like, let's say if we want to write 7 in this form, then 7 can be written as 4 into 1 plus 3. Similarly, like 151 can be written as like, let's say like something like 4 into 37 plus 3 or something like that. So yeah. So one basic thing is that any number can be written in form of 4k plus r. Now what we want to show is that choose the values of R for which this number can be a perfect square. So now any number can be written in the form 4k plus R. So, but let's say a and there will be a unique representation of that number. Like the number 10, the only way in which it can be written is 4 into 2 plus 2. Like assuming R is between 0 to 3 only. So there will be a unique representation for every number. So now the question asks choose the value of R for which this number can be a perfect square. So for a number to be a perfect square, uh, uh, what do we actually want? So let's just say maybe uh, so what I'm trying to say is that so whenever so the question is basically asking so a number like let's say a number 11 can be written in the form like 4k 4 into 2 plus 3, but 11 is not a perfect square. So maybe there exists a classes of numbers like let's say for values of R equal to 2. So let's say any number which is written in the form of 4k plus 2 will not be a perfect square, or whether it will be a perfect square or not. So the problem is something like this, that basically what can the perfect square, like if a number is a perfect square, then what possible values of R can that number take? Like let's say if a perfect square is let's say 4, 4 is a perfect square because it's 2 square, right? So 4 can actually be written as 4 into 1 plus 0. So in that case, R takes a value of 0. So we know that for value of R equal to 0, this number can be a perfect square because as the case is with 4 exactly. And similarly, let's say consider number 3 square, which is equal to 9. So 9 can be written as 4 into 2 plus 1. So now here the value of R equal to 1 in case of 9. So again, we can see that uh, for R equal to 1 also it can there exists a perfect square for which R equals to 1, right? So now we want to sort of show something like what while my claim is that any perfect square can only be of the form 4k or 4k plus 1. So note that any number can be written as like a number, any normal, like any natural number will be of the form 4k or 4k plus 1 or 4k plus 2 or 4k plus 3. But what I'm claiming is that any perfect square will only be of the form 4k or 4k plus 1. The 4k plus 2 and 4k plus 3 forms can't be for perfect squares. So this does not mean that any number which is of form 4k will be a perfect square. Because like let's say the number 8 is not a perfect square, but it can be written in the form 4k. But what I'm claiming is if a number is a perfect square, then it can be written as 4k or 4k plus 1. So this is what I'm trying to say. And how can we prove this? To prove, so let's say, or maybe I will say proof. So first of all, we know that it can, like, what's an example of a number which is a perfect square and is of the form 4k? So an example of that number is 4. Similarly, an example of a number which is a perfect square under the form 4k plus 1, example of that number is 9. And now we have given an examples for both 4k and 4k plus 1, but we also want to prove that uh, no perfect square will be of the form 4k plus 2 or 4k plus 3, right? So we basically want to prove that the perfect square can only be of these two forms, and no perfect square will be of the form 4k plus 2 or 4k plus 3. So let's just prove it. So it's a bit easier. So any number, take any number n, take any natural number n, take any natural number n. So I'll prove this for all natural numbers, right? So since So n can be written as basically, maybe I just type as capital N, and n can be written as, n can be of the form. So basically, n can, since n is an arbitrary number, so n can be of multiple forms. It can be basically of form 4k plus, it can be of form 4k, it can be of form 4k plus 1, it can be of form 4k plus 2, it can be of form 4k plus 3. So any natural number can be of these four forms. And now I'll try to see whether any perfect square is only of these two forms. I'll try to prove that a perfect square is only of these two forms. So how can we do this? So we take any natural number n, and n can be of the form 4k, 4k plus 1, 4k plus 2, 4k plus 3 only. And we also know that a perfect square, like I'm just assuming perfect square are squares of natural numbers. So also uh, a perfect square will be will be equal to, so perfect, what is a perfect square? Perfect square is basically square of a natural number, right? So perfect square will be equal to n square for some n, right? So like 9 is a perfect square, and it is 9 is a perfect square because it is a square of 3. 9 is equal to 3 square. Similarly, 25 is a perfect square because it is equal to 5 square, right? So basically, since we have seen that n is of the form 4k, 4k plus 1, 4k plus 2, or 4k plus 3, so now n square can be of the form uh, so since n was of this form, since n was 4k, n was 4k plus 1, 4k plus 2, 4k plus 3. So if n was 4k, then what will be the value of n square? It will be equal to 4k whole squared, which is 16k squared. I hope this makes sense. Similarly, maybe I'll just write it as first 4k whole squared. Similarly, it can also be of the form 4k plus 1 whole square, can also be of the form 4k plus 2 whole square, can also be of the form 4k plus 3 whole square. So I hope this makes sense. So let's just expand this out. So this will be equal to 16k square, right? And now what can I write? I can write the 16k square as something like 4 times 4k square. Let's just take case by case analysis. So I can write it as 16k square as 4 times 4k square. So now what do we know? Since this k was also basically an integer, because this 4 in this 4k plus r k is also an integer, or let's just say a whole number. So k is also a whole number. So k square is also a natural number, and so 4k square is also a natural number. So we can just write it as, like, let's just say 4k square. We can write it as something like k prime. So this is of the form, let's say 4 times k prime, right? So basically, do you see that what we wanted to prove that was that perfect square can only be of the form 4k or 4k plus 1. So basically, it is either divisible by 4 or it gives a remainder of 1 on division by 4. So we have seen in that in this first case, it is actually of the form 4 times some k prime. So it is actually divisible by 4. So for this case, we have proven, like for this case, like if n was equal to 4k, then for that case, we have proven that the perfect square will be of the form 4k prime. And similarly here, for 4k plus 1 whole square, I can expand it out as a plus b whole square. It will be 16k square plus 8k plus 1. And now this can be written as, like, I'll just take 4 out of these two terms, and this can just be written as 4 times 4k squared plus 2k. And I can take this one outside. So this will be plus 1. And now if I take this 4k square plus 2k as some k prime, then it will be like 4k prime plus 1. So do you see that in this case, on division by 4, if n was equal to 4k plus 1, then the n square on division by 4 will give a remainder of 1. So here the n square is of the form 4k plus 1. I guess k is different here, k is k prime, but this is just notation, right? K prime, everything is just notation. So similarly for 4k plus 2 whole square, I can expand it out again. It will be 16k square plus 16k plus 4. And now I can take a 4 outside for all of these terms together, and this will become equal to 4 times 4k squared plus 4k plus 1. So now this is again an integer, and I'll just write as k prime. So this will again be equal to 4 times k prime. So in this case also, it's like of the form 4k divisible by 4. Now, like lastly, come to the last type. So I hope whatever I'm doing is making sense to you guys, because if it does not, then you can stop me and ask me, like as always. So yeah, so this will be something like this plus 24k plus 9. And now I can write this 9 as something like 8 plus 1 and take 4 common. And what I'll get is 4 times 4k squared. So you can just do this calculation yourself also, it's not too difficult. Plus 2 and plus 1. So I can just take 4 common out of this, and from this 9 I can write it as 8 plus 1, and I'll arrive at this expression. So now again taking this as some k prime, this will be of the form 4k prime plus 1, because this one is extra. So I hope it's so Nimita, k prime is just some other number, like I've just represented this. Like for in every case, I've just represented, like I've represented here 4k prime, 4k square as k prime. Here I've just represented 4k square plus 2k as some k prime. I've just like to shorten this expression, like to not write it fully, I've just written that as k prime. Because the aim of the game was just to show that any number, any perfect square can be written in form 4k or 4k plus 1, right? So this k is just a notation, right? Maybe I should have written it a bit differently so you guys don't get confused with notation. So maybe I'll just change it a little bit. I'm sorry for this, but I'm just changing the notation a bit so you guys don't get confused. And instead of this k prime, I'll just write a k. So yeah. So what I'm trying to say is that now what we are trying to say is that any perfect square can be of the form 4k or 4k plus 1, can only be of this form, where k is some integer, right? Where k is some integer. What we are trying to show is that any number can be of the form 4k or 4k plus 1, where k is some integer. And we know that any number n can be written in form 4x or 4x plus 1 or 4x plus 2 and 4x plus 3. And now squaring for all these cases, I get some of these. And so basically what I'm trying to say is that in the case 1, I'll take this 4x square as the k. And so I'll say that in this case, if the number was of the form 4x, then I can write it in the form 4k, where k will be equal to 4k square. And similarly, if the initial number was of the form 4x plus 1, then I can write it in the form 4, then its square can be written as 4k plus 1, where k will be like this. And similarly here and here. So I hope this notation now makes sense a bit more. Okay, so it's clear, Nimitha, right? Uh, Is there some doubt, Nimita? Okay, sure. If no problem, then I guess we can move forward. So, so also like you don't need to apologize for asking doubts, right? Because like answering the doubts is my duty, and like having doubts is a good thing because it means that you're paying attention and like thinking about stuff. So yeah, no need to apologize for doubts. So keep that in mind. So yeah. So basically, so what we have proven is that whatever be the, so n can only take one of these four values, and whatever be the value of n, in all the cases, we can write its perfect square as either 4k or 4k plus 1. So what we have shown is that hence any perfect square can be written as 4k or 4k plus 1. So what will be the, and like what is an example of a perfect square which can be written as 4k? The example is like 4, because 4 is a perfect square and it is like 4 times 1. Similarly, what's an example of a perfect square which can be written as 4k plus 1? It's 9, because 9 is just 3 square. So the correct answer for this question will then be the value of r for which this number can be a perfect square. The correct answer will be basically 0 and 1. So correct answer is A and B. A comma B. So yeah. So since we are a bit short of time, I'll maybe reduce the number of questions which we'll be discussing. So yeah. So yeah. So now let's just come to the sixth question. So the sixth question is saying again it's a prove or disprove statement. So we should either prove this statement or disprove this statement. And statement is every natural number can be written as either the sum of two perfect squares or difference of two perfect squares or both. So again, like first of all, looking at the problem, understanding the problem is, in my opinion, as much important as trying to find its solution. So what the problem is saying is that so every natural number, so given any natural number, it can be written as either the sum of two perfect squares or difference of two perfect squares or both. So it's basically saying that we need to prove or disprove the fact that given any natural number n, can we write it as sum of two perfect squares, or can we write, is it possible to write it as sum of two perfect squares or difference of two perfect squares or both? So the problem is just something like this. Like given any natural number, like like for some specific natural number, like if instead of this question, the question was, let's say there exists a natural number which can be written as either sum of two perfect square or difference or two or both, then it's very easy to do, because like let's say we can find one, like we can just take two numbers, like let's say 2 and 3, and like just take their sum. So the sum will be like two, sum of their perfect squares will be like 2 square plus 3 square, which will be equal to 13. So basically 13, the number 13 can be written as sum of two perfect squares, right? Because 13 is equal to 2 square plus 3 square. So we know that some natural number can be written as either sum of two perfect squares or difference or both, because that some natural number can be replaced by 13. But what we actually want to prove here is that every natural number can be written. So one, we should be able to write one as sum of perfect squares or difference. And similarly, we should be able to write two as a sum of perfect squares or difference. Similarly, three, similarly, we should be able to write four also, five also, six also, seven also, eight also, and so on, if we want to prove this. So is the question clear, first of all, Nimita? Okay, nice. It's clear. So, by that, so if we want to prove this, like this statement will either be true or false. So if we want to prove it, then we'll need to show that for every value of n, this is true, right? So I'll just read the last question which I was. So for every value of n, this is true. Either we need to, if we need to, for any proof, generally we need to prove it for all possible values of variable, right? But to disprove something, we just need to find out an example where this does not hold. So it's not clear whether this statement is true or not. But what do you think? Like just take 2 minutes and think uh, like maybe just to think on a disproving side. Can you think of some natural number which can't be written as sum of two perfect squares or a difference of two perfect squares? Oh, so you think that we will be able to prove this thing? So actually, the claim is incorrect. Actually, so uh, the given claim is incorrect. So actually, we'll be able to disprove this. Incorrect. And why is the case? Let's just take the number. Take the number 7. Like 7. Just consider number 7. This is considered number. Consider the number 7. So not 7. Just let me think a little bit. So every natural number can be written as sum of two perfect squares or difference of two perfect squares or both. So what we'll try to do is, okay, so maybe let's just go through some thinking process first, right? Let's just not arrive at a solution directly. So what I'm trying to say is here is that, so then let's just try to prove this claim. So sometimes how if we don't know maybe like whether this claim will be true or not, like here we need to either prove this or disprove this. So when we don't know whether the claim is correct or incorrect, what general approaches are like try to find some counter examples or maybe just start and try to prove the statement. And if some at some step you get stuck, maybe at that point you can obtain a counter example after that step. So let's just try to prove this. So maybe a good way to prove this will be consider. So basically, we need to say that for all n, like for all n, n is the natural number, where n is a natural number. Uh, n can be written as either sum or difference. N can be written as sum or difference of two perfect squares, right? So this is something which we are trying to solve. So maybe we can take the case, suppose for like the for all natural numbers, like the n can either be odd or n can be even, right? So let's just take two cases. So case one is uh, that let's just consider n is odd, right? So if n is odd, then my claim is n can always be written as difference of two perfect squares. So maybe I'll just write it down. So if n is odd, so if n is so first of all, we know that if a number is odd, then it can be written as in the form 2k plus 1, right? Then n is equals to 2k plus 1, right? Like we know that if a number is odd, then it can be written in the form 2k plus 1. And now what I'm claiming is that uh, now like in this case, n can always be written as difference of two perfect squares. Now this is my claim. And do you guys see what will be the two perfect squares whose difference will be equal to 2k plus 1? For this case, do you know if two perfect squares exist whose difference is actually equal to 2k plus 1? So see, we are considering this case where n is odd. So we know that n can be written in the form 2k plus 1, right? Till now this is clear. Now, what I'm claiming is that this 2k plus 1 can always be written, this 2k plus 1 can always be written as difference of two perfect squares. Like there always exist two numbers x and y such that x square minus y square will be equal to 2k plus 1. So can you think what are these x and y for which their difference, for which x square minus y square will come out to 2k plus 1? Maybe since we are a bit short on time, I'll just give you this and maybe you can think about it later. So the two numbers are basically n equals to n equals to k plus 1 whole square minus k square. Like you can see this that this is because n is equals to k plus 1 whole square minus k square. Because like you can expand this k plus 1 whole square, it will be k square plus 2k plus 1 and reduce subtracting k square from it, we will only be left with this 2k plus 1. So there are these two numbers k plus 1 and k. So k plus 1 whole squared and k squared are actually perfect squares. So the difference of these two perfect squares is actually equal to 2k plus 1 indeed. So is it clear? Is this place clear that if n is odd, then it can always be written as difference of two perfect squares? Okay, so I'll repeat again. So I'm considering just that n is odd. So n can be written in the form 2k plus 1, right? Because any odd number is of the form 2k plus 1. Now what I'm saying is that this number n can be written as the difference of two perfect squares. Like what we want to prove or disprove in this question is exactly this, right? That any natural number can be written as either sum of two perfect squares or difference or both. So if we are able to show even that it's a like it's a difference of two perfect squares, then also we are sort of done because we need to show either it's sum or a difference. And we have just shown that it can actually be written for all odd numbers. It can actually be written just by difference. No need for sum also. Uh, that every n which is odd can always be written as difference of two perfect squares. And what are the two perfect squares? This k plus 1 whole squared and this k squared. So k plus 1 whole squared is a perfect square, right? Similarly, k square is also a perfect square. And difference of these two perfect squares, k plus 1 whole squared minus k square, will come out to like you can expand this k plus 1 whole square as k square plus 2k plus 1, right? And this k square will be subtracted. So we will only be left with this 2k plus 1. So what we are essentially saying is that this n is equal to k plus 1 whole square minus k square. And what this essentially means is that n can always be written as difference of two perfect squares in the case when n is odd. Are you able to understand? Okay, you are able to understand. Nice. So Now this, so if n was odd, then this claim was true. Like this, this claim was true when n was odd. So now the case two is at least, so n was even. So when n is even, we need to show whether for n is even whether it is true or is it false. So if we want to, like, suppose, let's say, disprove this claim, like let's say if we want to disprove even, then also the number for which this will be disproved, for which we would be able to disprove this, would be an even number, because for odd numbers we have proven. For even numbers, either we need to prove or we need to disprove this claim, right? For odd numbers, we are done that we have proved, but for even numbers, we are not sure whether we'll be actually able to uh, prove it or whether we'll be able to disprove it, right? So we'll need to think about what will be the case and when n equals to 2k. So my claim here is that actually in this case, there exists an even number which can't be written as sum or difference of two perfect squares. So my claim is, like, even though we were able to prove this in this case where when n was odd, but for when n is even, we won't be able to prove this. Like, we can find an example uh, where we won't be actually able to prove this. So that example can be basically, you can think, I think an example which would fit the bill would be yeah, let's just think of the number 4, maybe. Consider n equals to 4. So this 4 is an even number, and we'll show that this 4 won't be can't be written as sum or a product, a sum or a difference of two perfect squares. And like, it's easy to see that this 4 can't be written as sum of two perfect squares, right? Uh, and why is this the case? Because, like, we are considering only perfect squares of natural numbers, as I say. So maybe let's just do this. Okay, I'm a bit confused myself. So sorry. 6, 2, 3. Yeah. So let's just take this n equals to 6 instead. So you can easily verify that. So my claim one here would be, so let's say, like, consider the number n equals to 6. So it's an even number. And now what I'll try to show is that now we'll show that 6 can't be written as sum or uh, difference of two perfect squares. So we'll show that 6 can't be written as the sum, or it can't be written as the sum. It can't be written as the difference also of two perfect squares. So how will we do this? So first I'll show that first we'll show where's the claim one here will be that 6 can't be written as sum of two perfect squares. So to show that 6 can't be written as sum or a difference of two perfect squares, we'll need to show individually that 6 can't be written as sum and also 6 can't be written as difference, right? So I'll show two claims. That claim one would be that 6 can't be written as sum. Claim two would be 6 can't be written as difference. Okay, so 2 perfect squares. So we'll divide our proof into these two cases. And for this claim one, like 6 can't be written as sum of two perfect squares. This is sort of very easy to see because the since perfect square is always positive, so if 6 was a so the only perfect squares whose sum can be like the only we need to check for the perfect squares which are less than 6, right? Uh since perfect squares are always positive. Like let's just say if 6 was indeed able, if we like I'm just giving you some intuition. So let's just say if we were able to write 6 as some sum of two perfect square, like let's say we were able to write 6 as sum of two perfect numbers x and y, so that like 6 is equals to x square plus y square. Then since y square is positive, since y like perfect squares are always positive, so we can say that x square will have value less than equal to 6, right? Uh, in like if we were able to write 6 as sum of two perfect square x square and y square, then x square will individually be less than equal to 6, and also y square will also be less than equal to 6. But we know that the only perfect squares which are less than equal to 6 are 0, 1, and 4. And you can see no two of these perfect squares can add to 6. Uh, was my argument clear? I gave it uh, in a bit heuristic manner, but did my argument make sense? Okay. Okay. So I'll just write that this part is easy to see. So we have proved that 6 can't be written as sum of two perfect squares. We'll also need to prove that it can't be written as difference. Only then can we say it can't be written as sum or a difference, right? So for this, we'll use something like contradiction. So we will, so I'll cover this a bit fast and by contradiction. So suppose we were able to write 6. Suppose we were able to write 6 as difference of two perfect squares, x square and y square. So you must be familiar with the proof by contradiction. Here we assume that the thing which we are trying to actually prove is actually quite not correct, and then we arrive at something at a contradiction. So yeah, suppose we were able to write 6 as difference of two perfect squares, x square and y square. Then what can I say? I can say that then 6 is equals to x square minus y square. But this x square minus y square can be written as the a square minus b square identity we already know. It can be written as x minus y times x plus y. Right. So note that x was an integer, y was an integer. So this x minus y will also be an integer, and this x plus y will also be an integer, right? So also, since 6 is an integer, like 6 also will have some factorization, like 6 can be factorized as either 1 into 6 or 2 into 3 or something like that. So what we can say is that in like uh so suppose we write 6 as like let's say 1 into 6, 1 times 6, then x minus y should be equal to 1 and x plus y should be equal to 6. And from that we'll be able to see that x and y won't be integers. So basically, maybe I should write a bit more. So 6 is equals to x minus y times x plus y. Since x minus y and x plus y are integers and x plus y are integers, they will be divisors of 6. Like, do you see? Like 6 is equals to x minus y times x plus y. So basically 6 upon x minus y will be equal to x plus y. So x minus y will actually be a divisor of x plus y will actually be a divisor of 6. Similarly, x minus y will also be a divisor of 6. And also we know that the divisors of 6 are, since divisors of 6 are like, let's say 1, 2, 3, and 6, only these are possible divisors of 6, right? So you can just check for all of these cases, like you can put x minus y as 1 and x plus y as 6, and since x minus y as 2 and x plus y as 3, and you can just check that we won't be, from those equations, we won't be able to get that x and y are integers. So I'll leave this, I think since we are running a bit out of time, so I'll leave this proof a bit as it is, and I'll try to follow it up in the, like explain it a bit more in the next class. So the main idea here is that 6 can be written as difference of 2 squares. So it can be written as x minus y times x plus y. And since x minus y and x plus y are integers, they will be divisors of 6. And divisors of 6 are only 1, 2, 3, and 6. So we can just mix and match the cases. So since x minus y is a divisor, it will either be equal to 1, it will either be equal to 2, 3, or 6. Similarly, x plus y will also be equal to either 1, 2, 3, and 6. And we'll be able to see that in all the cases, we'll be able to arrive at some contradiction. So is the direction of the proof clear, like high level idea? I'll discuss it in a bit more detail in the next session starting. But Nimita was the, okay, so thanks. So yeah, now we will be able to arrive at a contradiction. So this is a sort of a high level idea from which we can derive a contradiction. So yeah, I guess this, from this we'll be able to disprove this statement, disprove this statement. So hence disprove. Yeah. So I guess we have like quite exceeded the time limit by quite a margin. So sorry for that. So these are the 6 questions which we discussed today. So I hope you enjoyed the session, and we'll be meeting this time like 6 to 8 only on next Tuesday. And we'll discuss this problem and this problem again, the last problem, in a bit more detail, and some more new problems. So yeah, thanks for coming and hope to see you next week again. So bye bye.